Hi, I'm Justin Hensley. I'm a senior member of technical staff in AMD's office at the CTO, and in particular, I work in advanced technology development. Today, I want to be talking about OpenCL, and this is the second video in a series of videos where we talk about how you can use OpenCL to accelerate applications, in particular using AMD's OpenCL runtime. We're going to continue talking about what is OpenCL, and in particular, we're talking about what is the platform and memory models of OpenCL. In other videos, we talk about the language used in OpenCL and how to actually create resources and compile your code. Just a quick review. The global and local dimensions of a problem, let's say in this case we're going to process an image. So the global dimensions of this image would be 1024 by 1024, and that's the whole problem space because we're operating on a 1K by 1K image. Further, we've decided that the best way to execute our problem is using work groups of 128 by 128. Those are going to be executed together, and again, recall that these are work groups. So as we're processing the image, each of these work groups is going to be processed together on the same compute device. And it's key to note that two work items within a work group can synchronize. And they can synchronize using things such as barriers and memory fences. But if we have work items in two different work groups, we can't synchronize those two together because they're not in the same work group. Let's talk about the OpenCL platform model. So a host is connected to one or more OpenCL devices. So if we look here, on the bottom of the slide, we have what is a host. So the host would be just your computer. So that's any CPU that runs your standard operating system and your application. So that host is going to be connected to one or more OpenCL devices. And in this case, an OpenCL compute device would be something such as a GPU, a DSP, or even a multi-core processor. It's just anything that's going to provide processing power for OpenCL. So our OpenCL device is further divided into OpenCL compute units, and those are shown in blue here. So a compute unit is composed of one or more processing elements. In that case, these are denoted in red. So our processing elements can execute code in a SIMD or single instruction multiple data, or even a single program multiple data model. Now let's look at the OpenCL memory model. So again, we'll start with our host here on the bottom and our compute device. Our host processor has some host memory. So this is memory that's on the CPU and accessible by the CPU. Our compute device has a global memory as well as constant memory. This is not synchronized. So when we access this memory, it is not synchronized, and we have to be very careful using it within a single kernel. Between kernel calls, we can use events to make sure that the memory has been synchronized. Each work item has a private memory, and it's termed private because only a single work item can access that memory. So work items cannot access each other's private memory. Each work group also has a local memory, and this is shared within a work group. So any work item within a work group can access this local memory and actually share data. It is important to note, though, that synchronization is up to the developer. You have to explicitly synchronize your memory to make sure that your memory accesses happen in the order that you want them. Memory management is explicit, so it is up to the user to actually manage when memory is synchronized and how it is synchronized. And also, the user must explicitly manage data to and from global memory. So you might be asking yourself, well, this sounds like it's kind of tedious for me to do. But it's actually not that bad. And also, it's very important for you to be able to manage this explicitly so that you can get the most performance out of the device that you can get. So let's talk a little bit about OpenCL objects. So there are four basic objects that we'll be talking about right now. The first are what I'm going to call setup objects. So these are things such as devices, context, and queues. So devices are simply things such as GPUs, CPUs, or other OpenCL devices. A context is a collection of devices. And you have queues, and these queues let you submit work to the device. You have memory objects, and there are two basic types of memory objects. You have buffers, and these are just basically blocks of memory. And you have images, and they are 2D or 3D images. And if you're familiar with OpenCL program, they would be analogous to 2D and 3D textures. You have execution objects, which we've talked about previously, and those would be programs and kernels, where a program is a collection of kernels and is very similar to a dynamic library, and kernels, which are the actual code that's going to be executed and the associated arguments for those kernels. Finally, we have events, and these events are used for synchronizing and profiling your data. So in this case, we have an AMD GPU and an AMD CPU device, and we have a single context that is talking to those two devices, and we've created two command queues that allow us to submit work to both the ATI AMD GPU and the AMD CPU. So let's assume we have a context, and this context has two devices in it. On the left, we have an ATI GPU, and on the right, we have AMD multi-core CPUs. So how would we actually submit work to these devices? Well, there's three basic steps that you're always going to use. The first thing you're going to do is you're going to compile code. After you've compiled that code, you're going to create data and set your arguments. After you've done those 3 easy steps, you'll have executed an OpenCL program. So let's do the first thing. So the first thing is we have program objects, which will take our source code. We'll actually build those programs once we've loaded the source code from disk or we've loaded it from a string. We're going to get a kernel object. So our kernel object will have the actual code that's going to be run on the different devices, as well as the arguments to those kernels when we execute those kernels. So once we've compiled our code, created our kernel objects, now we need to create some memory. So we're going to create memory objects, and you might be creating images or just buffers. Sometimes you might only do images, sometimes you might do buffers, sometimes you might do both. Once we've created some data, we have our kernels to execute. We're going to use command queues to in-queue work to our different devices. So it's key to note that our work is queued in order, but depending on how we've created our queue, it could be executed out of order or in order. And the key thing here is that with an out-of-order execution, the runtime will make a decision as to which kernel it should execute when it feels it is best to execute it based on the current resources. So it is very important to use events in that situation to make sure that your kernels are actually executed in the order that you want them, because if you have dependencies between your kernels, you need to make sure that those dependencies are met using events. Once again, this is Justin Hensley, and I thank you for watching this video, and I hope you'll watch the rest of the videos where we talk about OpenCL and how you can actually accelerate applications. Thank you very much.